So I think that should be good. I'll just shrink this a bit so it's on the side. But yeah, welcome to FRC Subsystems and Mechanisms. If at any point, if you guys have questions or anything like that, feel free to just ask in the chat. And that question will be brought up to me. It doesn't really matter when you ask questions, you can ask throughout the presentation. And then I have some time at the end as well for you guys to ask more questions. So let me go over a little bit about myself. I actually am a mentor in Canada, and I'm part of FRC 1241. And I used to be the lead engineering mentor. Now I've taken a slight role back. But essentially, I'm a graduate of University of Waterloo. I studied mechanical engineering there. And I was a student in FRC from 2007 to 2009. And then now I've moved into the mentoring role. So I've been with the team, 1241 and 1285, for about 15 years. And currently, I work at a company called Gypsum Technologies, where I'm a mechanical engineer there. And what we design is heavy machinery that makes drywall and cement. So let me go over what we're going to do today in this conference. The first thing is what I'll go over is kickoff and what to expect during kickoff when the game release happens. Then we'll go over a little bit about strategic mechanism selection. So different types of mechanisms that you can use for different aspects of the robot. I'll go over some tips for designing. I'll share some design success stories. And then I'll go over some of the common suppliers and some documents that you guys can use in the future. So then this way you have more information after this conference too. So the first thing is just the importance of Kickoff Weekend. I'll show you guys what 1241 and 1285 do as part of their kickoff, because we believe that usually the more quick you are with your decisions and being able to start actually prototyping and also designing your robot and finishing the robot gives more time for the programming team to actually take it and start building their code and making it a lot smarter. So we try to make sure that the kickoff weekend is very efficient. We don't want to have too many lingering ideas. We want to make sure all the ideas are on the table for what type of robot you want to make. But then you also want to make decisions as quickly as possible so you can move on and start designing the robot. So the decisions that are made during kickoff essentially dictate the rest of the design period for us. So the first few things that we try to decide during that one weekend is the drive chassis, or what type of drivetrain we want, the strategic capabilities, so essentially what the robot should be able to do. So whether you want to score a high goal or a low goal, for when it was the 2019 game, if you want to work with the balls or the hatches, like whichever one or both, and which level you want to score on. And then finally, we also want to decide what type of mechanisms we want to prototype. Now, some of this stuff can be applicable to rookie teams. Some of them can be applicable to senior teams. And we want to make sure that when you guys are using this, you want to take time so that everybody feels like they've contributed, but also making sure that everybody is on board with the decision. So generally speaking, we want to make sure that the entire team is deciding together, but also believes that the robot that we've chosen is the one that they want to make. Otherwise, you're going to have a lot more conflicts where some students or some mentors and things like that don't believe in the robot design. So then it actually kind of doesn't seem like a good experience to it. Yeah. So here's what our kickoff schedule looks like. We divide it up into Saturday and Sunday and what we need to do in both days. So on the first Saturday, we do all the possible movements and functions that you need for the robot. So list everything out. Whatever a robot can possibly do, you want to make sure that you write it down and you have an entire list of everything a robot can do. So for example, last year, it could be pick up balls from the floor. It could be shoot into the high goal. It could be shoot into the low goal. You could also hang on the truss, or you could, 2 years ago in 2020, when they had it, you could, I think we called it the Wheel of Fortune, but essentially you could spin the colored disc so that it lands on the color needed. All those things are capabilities. You want to make sure that you can drive around. That's one of the main big ones for playing an FRC game. But all the movements, no matter what they are, you should write them down. Then what we do is we actually, on that Saturday, we also choose which movements and functions we want to do. The reason why we choose this, and we don't talk about mechanisms and stuff like that, is one big thing that people believe in is that your robot mechanisms should dictate your design, but that's not really true. A lot of the top FRC teams, what they do is design based on strategy. So they choose based on movements and functions rather than a physical part or a mechanism dictating what their robot does. So what I mean by that is you should choose to score in the high goal rather than thinking about how you're going to score in the high goal. Because then the following day, when we discuss the intake, the tool, and the end game, we can focus on making sure that any design or any idea that we come up with would be able to meet the requirements that we determined on Saturday. And then we also start beginning to collaborate designs. So maybe one mechanism with another mechanism combined together kind of really work better. So then we decide that. And then your drivetrain should be decided by this point. So whether you want to go West Coast drive, which I'll go over today, or if you want to try to do a swerve drive or holonomic and all these different kinds. And then what we do is we set prototype variables for each proof of concept. So what we do is essentially you can think of it as like lab testing your prototype to making sure that it meets your accuracy, it meets your scoring abilities, it's making sure that the balls don't jam inside your prototype, those kind of things. And those are some of the things we decide to. And then finally, we start just creating some geometric studies so that we know how big different aspects of the robot need to be based on what we chose. So yeah, it's a lot jam-packed into one weekend, but ideally you could spread this out over 3-4 days, depending on how much you can meet at school or how much you can meet online. But it's good to go through this before you even start building anything. Reason being is then this way you at least know what you're going to make in terms of the prototypes. Otherwise, you could be wasting time that is valuable for finishing the robot earlier. This is what I mean by list all possible movements. Essentially, it's everything that you could possibly do. So once you do that, sometimes if it's applicable in the game, we also decide something called robot roles. So what type of robot do you want to be? So this is a chart from 2017 where you could have 3 different options for a robot design. You could be a gear robot that can hang. You could be a ball shooting robot that can also hang. And then you could have a ball gear hang robot that could do all of it. So essentially, we decided to go with the ball gear hang towards the end. But what happens is you decide the pros and cons for both. And then you try to actually create some of the complexities and discuss it and stuff like that. So this number here determined actually how many students had voted for which one they preferred. So now it was 11 versus 6, but that wasn't the decision maker. What we had to do is see if there are any points that the 6 had that all of us that were in 11 would move over here. So it would only make sense once everybody, the 17 of us in that particular time, would all be under one category. We wouldn't move on our discussion until that was done. So it makes sense for bringing up all the points. And there are often times where the people with less votes actually are able to convince the people with more votes to come to their side. So we try to make sure that everybody is on board with whatever we decide. Now, once you actually get all your robot movements, you want to actually categorize them into needs and wants. So needs, you absolutely have to do. And then wants are, you could have them, but if it is going to not work out, or maybe you're overweight with your robot, it's the first thing that gets removed. So a lot of top teams do this. Sometimes they have complex mechanisms or something extra. And if it's not important, then they will take it out. Do we have any questions so far about these two slides where we go over? And yeah, please let me know if I'm going too fast as well, just so you know.
No, we don't have any questions yet.
Okay, great. Thanks, Manya. Okay, so here's the example again for 2017, where we have the gear ball and ball gear hang. So here's where we had the pros and cons, and then we decided accordingly. Now we did end up going with the ball gear hang robot towards the end, but it was actually quite complicated to integrate everything together. And I think towards the off season, we actually went back and created a gear hang robot, which was even more strategic and more helpful in being successful. So not always the decision you make would be the one that you can achieve the best, but it actually is pretty cool to have everybody on board and having a robot on the field that you're proud of. So we're going to go over some movements and preferences. Now, one of the biggest things that I want to highlight is whenever you have an FRC season or FTC or FLL or whatever, the biggest thing is to have fun. So sometimes we love to goof around and try to create some fun moments for the students, the mentors, and everyone to kind of laugh together, just so that we know we can imagine the game in a fun way. So here's actually one of our mentors inside a noodle box, and he's playing the 2019 game. So he's essentially putting the hatch on, and then now he's actually trying to grab the balls and stuff like that. And then he's going to be moving it and start scoring. So it's really easy. This is one of the reasons why we figured that you have to pick up the balls off the floor, because going to the feeder station all the time is not always efficient. But yeah, what I want you guys to understand is like FRC seasons are supposed to be super fun and really difficult. So if you have time to goof around and have fun with it, by all means, make sure that you guys are able to do that. Okay, so movements and preferences, there are two portions of the game that are usually quite intense in terms of scoring points. And sometimes they actually help in being the deciding factor in terms of a win and a loss. So those two are the autonomous mode and the endgame mode. And sometimes you actually have some really big mechanisms in order to achieve both of these things that might actually need you to make that decision earlier so that your robot can compensate for it. Especially for endgame, you would need to dedicate some space. You need to dedicate some motors and things like that specifically for that, because it usually is quite a big mechanism. For autonomous mode, it doesn't usually require any extra mechanisms, but there are some that I'm going to show you today that allow you to actually score faster in autonomous. So this is 254's climber in 2013. What I'm going to do is just double check that I'm sharing with audio. So I'm just going to stop share for a quick second and then just share with audio. So then it's better. Yeah. Okay, we're back. So yeah, this one is a really quick video, but you can see that they essentially are climbing in 2013. It's quite a big.
Started from the bottom, now we're here.
So as you can tell, it's actually quite a pretty elaborate system of different elevator mechanisms and these cascading arms that actually come out, grab on, and then go up. You may have seen a lot of these type of telescoping arms in last year's season in order to grab on to level, but it was crazy that they had this all built in to be able to do it in 6 seconds in this game, because to fit that in the profile was actually very difficult to do. But you can tell that they have to dedicate motors, they have to dedicate space for all these arms to come in and out. So it's actually quite difficult. So this is another one where already had the suction cup mechanism in order to raise. So that is a separate mechanism to actually let them up on the platform at the end. So that's actually a very popular design in that year. Eventually, a lot of people were trying to adapt this suction cup mechanism, but you can tell that they have to dedicate robot weight to it and have that kind of system on their robot to be able to lift up and down. And you can see here, 254 had actually adapted that as well. They have gone over in some of their YouTube videos and things like that about why they ended up choosing this, so that they could actually get rid of some weight on their intake mechanism over there and create a much more efficient robot for that championship. But yeah, that's one thing also to keep in mind, is that as the season goes along, it's not a problem for you to start changing your design and trying to make it better and better based on what you see around. The only thing you have to make sure is that you are able to build it in time and also test it out before you put it on your robot, because you want to make sure that any change makes your robot better rather than accidentally create problems where it will actually hinder the performance. So here's a unique mechanism that we had in 2017. It's the auto gear holder. So this was the mechanism here that you see. A lot of teams actually had an intake on the floor and things like that. And we had a separate slot and eject mechanism at the front of the robot. But we kept this here pretty high so that our human player actually would take the prong and raise it up. And so when our robot actually goes and deploys the gear, it's actually much faster for them to pick it up and start doing the autonomous mode and getting the 2-gear auto happening. So because the human player had raised up the prong, it was less time for him to pick up the gear and put it into the slot or put it into the 2nd gear mechanism. And so it was a lot faster and a lot more efficient. And then we could actually start scoring balls into the hopper right after the boiler, I think it was called that year. So this is a very small passive mechanism. I think it was just 2 plates that were made out of Lexan, just holding the gear up here. And it was really instrumental in trying to keep us successful and getting us onto Einstein that year. Getting 3rd place in the world, but it was just so small and such a simple mechanism that you could add it and it would make a lot better performances in the autonomous mode. So it never has to be truly crazy mechanisms. It can just be a simple gear holder that can help win. So now I'm going to go over some strategic mechanism selection. But first, I wanted to just let you guys know that most robots in FRC are usually broken down into 4 different sections or subsystems. And then all of your design decisions and everything like that can fall under these categories. So there's the drivetrain, which is essentially responsible for moving your robot around. There's the intake, which is to collect or possess the game pieces. There's the tool, which is used for scoring the points or maybe manipulating the game objects, like they could go up and down. And then the end game, which is essentially your mechanism used for scoring points in the final portion of the end game period. So in drivetrains, some of the most popular ones that I'll go over today, the most popular one is called the West Coast Drive, or the tank drive is another way of putting it. And essentially it has two sides of the robot. They're independently driven. So you have a right side gearbox, a left side gearbox. And essentially when you want to turn, you can turn the right side gearbox one direction, left side gearbox the other direction, and then you would be able to turn in that direction that you want to go to. So it's really simple. It usually just uses simple extrusions and then just two gearboxes and some chain. Sometimes these are belt driven. And then it's actually really easy to start a drivetrain, and it usually is pretty agile depending on which wheels you choose. And then it's actually pretty easy to program as well, because it's pretty good at keeping it stable. The one thing that you want to make sure is that you want to choose, most of the time you want to choose 6 wheels or more, just so that the center wheels that are part of your chassis are slightly lower than the outer wheels so that you could spin much more easier. If you have all these 6 wheels at the same height, then what will happen is it will be very, very difficult to turn on carpet because all of these wheels have to slide a lot. But if you have these 2 center wheels, usually the standard drop is about 1/8 of an inch. If those 2 wheels are lower than the outer ones, it'll spin much faster. And that's the difficulty, is one of the easiest ones to come up with. Next one is this one here, where you have these sort of omni wheels or mecanum wheels that allow you to go in different directions without actually turning the robot. So this one here at the top is called the H drive. So essentially the wheels make an H. And what happens is if you want to go sideways, then these wheels will be activated. But if you want to go forward and backwards, then these 4 outer ones will be activated. And what's not good about this one is that it's really bad against pushing. So because these wheels don't have any rubber on them, they're all plastic, then it's actually really easy for an opponent to push you around. Top teams have used this before as well. And so what they do is they've learned to kind of like dodge the pinning or dodge any defense. So keep that in mind when doing this, is you can't really push through defense. You have to learn to drive around it. It's very good agility, but it's actually pretty difficult because programming more motors and things like that can be pretty hard compared to the first one that we went over with West Coast. But yeah, as you can see in this video, the robot can go sideways, it can spin on the spot and stuff like that, all because it has mecanum wheels. The next one, which is the most popular one now, but it is actually very, very difficult to program, is the swerve drive. So the swerve drive, you have 4 modules at each corner of the robot, and each module controls 1 wheel. It controls how fast the wheel is moving and also which direction it's being spun in. So you have 8 motors that you're dedicating for your drivetrain. So keep that in mind when choosing this system. But usually it's very good against defense as well, because you can both move around defense or you can push through them. But then you also have to use very hard programming tools because you need to make sure you have your gyros and encoders and everything working at all times in order for this to be successful. But if you can pull it off, then it's actually a really, really cool drivetrain. It's just very difficult to program and very difficult electronically to make sure that everything's being very efficient. So just keep that in mind. Now, a lot of top teams have released some programming code and everything like that for their swerve drives. So you can still use that, but you want to make sure that everything is built correctly as well. Now we're going to move on to some intakes. The one thing that I like to highlight in intakes is that you always want to make sure that it is a touch and go system. So most likely you want to make sure that it has some rollers in order to actually grab the piece and bring it towards you. But what you want to do is just make sure that the drivers have an easy time in grabbing the game piece. So what they should do is if they're near the game piece, they should just be able to touch it, and that will actually provide the intake, everything that it needs to grab the piece. The driver should not have to think about what they're actually intaking. They should just be able to drive around, because there's very little vision that drivers have for a game piece unless you have cameras on the robot. So it's actually pretty hard across the entire field to see where they're going. So if they don't have to see the game piece, but they know it's there, then it makes it easier for them to do it. Now, one of the things when you are gripping something, just make sure that there are some elastic methods to keep the mechanism secure and clamping onto your game piece. Otherwise, when you drive around, then you may actually lose your game piece if you don't have things there. So this intake up here is from 11-14 in 2018 season. So you can see that they have these big arms that are pneumatically actuated, and they have these wheels. But over here, you'll see that they actually use some button sensors so that when the game piece comes into this cavity, the intake knows to shut off the wheels. So that's a big bonus. They use some smart mechanisms here. But also, they have these pads here that essentially are actuated with really tiny cylinders to hold on to the game piece. So when they grab it like this, there's actually some force that is made by these grippy pieces in order to grab on. So it's really important to have that so that you have a secure game piece at all times. Otherwise, it may actually fall out of your robot. The next mechanism to choose also is the shooter. So this is essentially a way to score your game objects. I'll go over different types of shooters that are in this presentation today and what teams like to prefer. So first one is the catapult or elastic launcher. Essentially, you have a whole bunch of rubber bands, or you can use pneumatic cylinders in order to store energy and then launch the object. Just keep in mind that it needs to be reset after each shot. And so usually it has a slow fire rate, but it's got a really long range. So you can shoot from really far away. The difficulty is medium because you have to make sure that you have good mechanisms in order to work with the game object. And then you have to make sure that they're always accurate too. So here's a video of a catapult from Team 148 Robo Wranglers. So you can see that they actually are shooting the ball. So that part of the video was sped up. It actually does take a little bit more time for their catapult to come down. But you want to make sure that you can see that it always constantly launches the same way. So you can get pretty consistent with it. It's just it's kind of slow to retract down and launch again. The next type of shooter is the flywheel. So essentially, it's just a giant wheel that usually has some weight on it, extra weight that is used for increasing the inertia. But it's really nice because you can shoot a lot of game pieces a lot faster than a catapult. So if you had to shoot all of these game pieces that are inside this robot, the catapult would have to reset every time. But if you have a flywheel, it's just a big conveyor belt, but with a small wheel at the end. it allows you to really shoot fast and lots of gun. The only thing is when you do have the high fire rate, you also have to tune a lot. So you have to make sure that the robot knows how fast the flywheel is spinning. You have to use PID control to make sure the wheel is always spinning the same speed. So then you have consistency. So it's pretty difficult. And you have to do a lot of programming in order to make sure that this one works. The next one is the piston or the pneumatic launcher. This is different than a catapult. Essentially, it uses a cam mechanism with actually like almost like a poking stick, where it allows you to actually push on the ball. Usually the weakest because it has a low range. You can't actually transfer that much energy onto a game piece. And it doesn't get affected by ball variation, which is a good consistent thing. And it's compact. So it's pretty easy. You just have to make sure that everything is lined up properly before you launch. So this is 118's robot from 2014. And so they had this giant launcher that's actually retracted back and then used elastics to push forward. So this is another way of doing it. Now, this is something that I want to highlight was that in the shooters, now a lot of teams are also adapting the turret mechanism, which is where your shooter actually rotates on its axis. So then it's independent compared to your drivetrain. This is actually adds another level of complexity. You can see that this is 254s from 2016. This is 1241s from 2016. This is Citrus Circuits 1678. They have released their CAD, I think, last week for this robot. You can see how complex this turret system is as well. It just adds another level of complexity, and you need to make sure that you have vision tracking when implemented properly. So then at least you're making sure that this turret lines up. You also have to have a lot of safety parameters. So sometimes if your programming is not done right and this turret spins too much, then it's going to rip all the wires out, which you don't want. So you want to make sure that you have some safeties placed to limit the motion. And then also sometimes what we've found is that you actually want to put a dampener on the camera. When your flywheel starts rotating, this entire mechanism shakes a lot. So you want to make sure that your camera also has some rubber dampening so that it's not shaking. But you need a large amount of time to program this. So if you choose to do a turret mechanism, you have to make sure that you build it quickly so that your programming team has enough time to actually go through everything. And now I'm going to go over, actually, before I move on, do you guys have any questions about shooters or anything like that? If you guys want to bring that up now. Okay, I'll move on to the next section then. So the next section is called the mechanism selection, which is the lift. So these are usually just single or multi-jointed arms. And essentially it's good for rotating the game piece and lifting something up. You do need a sensor at each joint so you know which direction it's going and where it's placed. And then also you can make sure that the longer your arm is, the more powerful your motor or your gearbox has to be. So you want to make sure that you actually have some sort of springs or some sort of gas struts or things like that to offset the weight, because gravity will not be your friend in this case. The longer your arm is, the more your motor will be. But it's pretty easy to use a bar linkage or anything like that. You can get pretty complicated with it when you start adding more linkages in order to control the way the arm is swinging. So for example, here, this is a 4-bar linkage. So you can see that the container is always staying in very similar orientation all the way up. If you increase or decrease some of the lengths of the arms, then this rotation can be controlled in a different way too. Now, that's all based on geometry, so it's kind of nice, but you do have to make sure that an arm could be swinging a lot. So you want to make sure that it's very strong at the joints so that it's not rotating a lot, because it can be quite unstable when you want to do that. And one of the last few mechanisms to select from is also the elevator. So for the lift section, and this requires a lot of attention to detail. There's a lot of complexities in terms of how you lay out your bearings. And it actually is pretty fast. It's very fast. And it's really compact too. And it's actually pretty simple in terms of knowing where your positions are, because it's just going up and down. It's not following an arc motion like an arm or a bar linkage. So it's actually much more easier to think of it from a programming perspective. You're only going up and down with your mechanism. It's still difficult because from a mechanical standpoint, it actually gets pretty difficult to make sure that everything is sliding properly and there are no jams. And now telescoping arms, these have become really popular for end games recently. We saw a lot of them in the 2020 season and the 2021 season. And it requires much more attention to detail. It's actually pretty complex to have all of these mechanisms slide in and out of each other. And then since it's pretty fast, but because the stages fit into each other, it's very difficult to assemble. So you want to keep that in mind, making sure that it's actually one of the hardest things to accomplish, but when you do it, it's pretty satisfying to be able to have something so compact. These are some examples of Team 610 who put a telescope on their mechanism here. This is that 254 robot that we saw that can climb that pyramid in 6 seconds. This is what their mechanism looked like when it was actually closed. The next one for hanger and climber, what I wanted to show you guys is a winch. This is actually a really, really easy way to make sure that you can go up and down. It's good for taller hangs, usually slower than pneumatic hangers, but it's good for having a ratcheting mechanism so that it doesn't unroll itself. But it's really easy. It allows you to unwind and wind at the same time if you wanted to. And you just have to use a really strong type of aircraft cable or rope in order to make sure that the rope doesn't snap while you're actually rotating it. The next one is the piston or pneumatic cylinder. This was in 2013. It was a really easy way for 610 to actually climb. So it was just a short little pneumatic thing coming up, and then it would come back down in order to actually have the robot hang on the lower level of the pyramid. Super easy. So I have some tips for designing. These are actually some of the things that I really like to look forward to make sure that the team is focused and making sure that whatever we choose will be successful. The first point is that there's no right answer in the FRC game. You'll see a whole bunch of different types of robots, and they'll all be different in order to make sure you can still accomplish the goal. And there's no right answer. So whatever you choose and whatever your teams to decide together, it will be able to optimize so that it actually plays the game very, very well. So just keep that in mind. And that's why making decisions can be easier, because since there's no right answer, you can still go with whatever your gut feeling is and actually make it work. Just keep that in mind. There's no right answer. The next one is to keep things simple. Make sure that you're working with the capabilities of your team. If your team is very experienced and has a lot of designers and things like that, by all means, you can make a complicated robot. But if you don't have that, then it's okay to actually keep things simple and making sure that things like this robot here, that's from 2026, very, very, very complicated. Like it was able to pick up the 3 garbage cans. It was able to stack. all sorts of stuff. Very, very complicated, but totally unnecessary because there were so many other simpler robot designs that did the same thing that they did, but better without being so complex. Pay attention to the orientation of the game piece. So just make sure that whenever you pick up, you want to make sure that you know which direction the game piece is facing or things like that. And whatever your intake mechanism is, can be able to compensate for that. If your game piece needs to rotate in order to score, then keep that in mind, because then maybe you can incorporate that into your mechanisms to make it easier. Make sure that you grab the game piece easy and quickly. Remember, we called it the touch and go mechanism, is that your driver should be able to just go really close to the game piece. And when they touch it, it should come into your robot, no problem. So pay attention. Game piece possession is like the fastest way. And then when using arms or linkages, just make sure that you try and take the load off the motor. So you could use things like coil springs, gas struts, all these sorts of mechanisms in order to make sure that your motor is not feeling the gravity or the load that comes just from your arm being heavy. Use sensors wherever possible. So make sure that you're choosing these sensors early and putting them into wherever you need to. Just because anything that can be automated makes it less of a driver input. And so they don't have to think. Like the games that are in FRC are very high pressure situations. So the more that your driver has to think, the less efficient they'll be at choosing different things to do during the game. And that could cause issues. And then just make sure that you choose your designs using prototyping. So try to make sure that you're prototyping your designs so that you can see what works, what doesn't, and where a ball can jam or where the intake will cause issues. Don't just assume that it's going to work the first time. And then, like I said before, pay attention to your team's skill level and resources. So if you have all the parts in the world, then by all means, you can use a lot of them. But if you do have limited parts or limited skill level because you're a new team or things like that, keep things simple, and that will allow you to actually be very successful in the game. And if you want to improve your team, you may have to go outside your skills level. This is a caveat to this. So this is one thing that I notice is like, if you try to keep things simple and keep things in your skill level, your team might not grow. So if you're willing to sacrifice some winning percentage or things like that, you could actually experiment with something more complicated to improve your team and the knowledge of your team. But keep in mind, with higher goals, you can also be severely successful. So if you're trying something that is more impactful, then make sure that it is still successful. But keep in mind, if it's unsuccessful, that's not a bad season. It's just you were trying to grow your team further. So I'm going to go over some winning designs from over the years. In 2014, where there was using these really big exercise balls and shooting them into goals. 254 had a really cool 3-ball autonomous boot. So they grabbed all 3 balls in their robot and then were able to shoot it, which was really nice. Having that 2-ball autonomous or 3-ball autonomous was actually pretty crucial in making sure that the teams were successful that year. In 2016, there was shooting from really far away from the outer works, which was really nice because you could not be defended when touching this portion of the field. And also, when you're this far away, your cycles will be lower because you don't have to go as close to the goal. The other one was ball stealing. We could steal from the opponents when they were trying to feed out. This was really important this year as well, or in the 2020 and the 2021 season, where a lot of teams were hovering around their opponent's feeder station and being able to take balls from there to score. That's actually a really big time strategy to do it. And then one key end game was the hanging shot. So even when going up at the last second, you could score 5 more points, and that could be the difference between a win and a loss. I wanted to go over this robot here, which is from 971 from 2016. Before I played the YouTube video, you can see here that it's actually very complicated because it's got this entire arm mechanism, but all of this folds underneath this profile so that they could go under the low bar. And so it's a very, very successful robot because they had put all of this in there, but they have engineers from like NASA, and they have students that are really, really experienced with CAD and things like that on their team. So this robot was possible. It's actually very, very hard for someone to come up with this. So let me just show you this video. The robot starts here, and then it goes under the low bar, and you can see it actually unfolds itself, and then grabs another ball, unfolds itself again. And then you'll see that that was actually a different direction for the arm to move. So it's actually quite difficult for us to be constructed. But now you'll see it coming. You can see how complicated it is. There's so many things going on, so many bar linkages. But it can shoot from the outer works, which is really important because they can get opponents to give them penalties. They're not able to defend it. And I'll show you the end game as well, because they actually have ability to hang off the robot too.
Trying to pick up a boulder. Let's see what 3387 can do.
This is the whole ball stealing strategy, where they were coming to the opponent's feeder station and taking balls. And here's the end game that they had. So they even added an entire foldable hanging mechanism inside there.
Get that grappling on that top part over there. 1734 wants to do the same. Up goes 971. Up goes 1736.
Just way too many things going on in this robot. And what I want to show you guys is that this is the highest level of complexity that you can have with the robot. But there are so many other teams that did more simple robots than them and were more successful at doing all of these things. So there are some times where you have to sacrifice, like going under the low bar, but it makes the robot easier to make. This robot is very, very complicated to make. Some winning designs in 2017. There was the whole 4-rotor offense and defense, which mean that you would actually try to score all the gears that you could possibly do. And then after that, you would defend the other team so that they can't get 4 rotors. And that would give you a point swing of 100 points, which is quite a lot of defending to do in order to make sure that happens. The other key in autonomous mode was the hopper auto. So teams like 1114, they actually went to the hopper during autonomous, grabbed all the balls and started shooting. And because the fuel value was 3 times as much in autonomous, you could achieve your 40 RP easily, and you could get your 1 ranking point. So that was another strategy that was really good. In 2018, cube scoring on a moving or a losing scale was really important because Team 195 had an elevator that could go really, really high. So if they were losing the scale, then they could still score on top, which was really good. And then 254 had perhaps the best autonomous mode in all of it, where they scored 3 to 4 cubes on the scale. And that allowed them to get ahead of their opponent and pretty much go the entire season undefeated with that sort of mechanism, right? So it's really important to be able to design something that can do autonomous well, but also keep scoring when you're actually playing the game. That's really it for the winning designs that I have. A lot of the designs from 2019 and 2020 and things like that follow suit with a lot of these principles. So I didn't really go over them, but I do want you to research more, take a look at a lot of the teams. I know 1678 just released their CAD for their robot. So that's pretty exciting. You can actually take a look at it. They had very, very good, successful robots this year. So a lot of these top teams like to share their resources, and that's a great way to learn. These are some of our most common suppliers that we use in the team. So there's Vex Pro, West Coast Products, McMaster-Carr, Rev Robotics for motors, and then also AndyMark. So all of these are usually what we go to for any of these parts that we want to buy. Any metal or machining and things like that is all done in-house at our shop. So we usually don't send those parts out unless we need something laser cut. But apart from that, these are the ones where we buy motors and parts from as well. The one thing I wanted to go over is the robot playbook. So this is something that was started by Team 1241 and essentially is a step-by-step guide for everything that we do on Team 1241. It's very specific and it is public. We have it on our website, so you can print out a copy and you can do it. We usually have step-by-step dates as well as to when you want to complete things by. So then it's easier for your team to know what they need to do in terms of timeline. And you can get it at this website here and download it. It's the 2019 version, so you'll see that it goes over that year, but you can change the dates and use it accordingly. We found that this guide actually is continuously better and better. Now that there's no bagging rule, you could modify this to add an extra week or something like that in order to help you out in different areas. So just wanted to let you know that this is during the pre-no bag era. So you did have a 6-week timeline in order to complete the robot. But it does go over a lot of design tips, goes over mechanism selection, some historic performances, all sorts of things. And that's really it for my workshop. I know I ended a little bit early, but if you guys have any questions, feel free to ask now. If you want me to show something extra, then I can for sure do that too. But now is the time for any questions. This is my contact information. Feel free to note it down and you can send me an email. I will definitely reply to it. And if you need more conferences or something like that, just let me know. I'll be happy to attend and help things out. Yeah. Like I said, that's really it. If you guys have any questions, you can for sure ask now.
Well, first of all, thank you, Malavia, for your amazing conference. And now we're going to, they are asking if you can put the Playbook link in the chat.
Yeah, let's do that.
Please.
So I'll do that as well. But that should do that, yep. Any other questions?
Yes, I have a question.
Okay.
Our Ricky team is asking, what do you think about the AndyMark drivetrain?
Yeah. So the AndyMark drivetrain that gets given in the kit of parts is actually really good. I highly recommend using it because they've done a really good job at making it easy to build. And also you could swap out the motors really quickly and make it a lot more faster. So I think it comes with standard sim motors. You could swap that out for like Neo motors or Falcon motors, and it'd be a really good performing drivetrain. Like it's actually better than what most teams construct on their own. So yeah. And it uses belts too. So it's actually more efficient and it's a really nice place. Yeah. Do we have other questions?
Yeah. As a as a rookie who might not have like the same quantity of money that other teams might have, what do you think is the main thing they should invest on the robots, like to maybe give them some quality, even if they don't have the same amount of privilege?
Yeah, that's a good question. So one of the things that is really key towards success is making sure that you ask for teams' help from teams that do have the wealth and machine shops and things like that. So at 1241, we're pretty blessed with our own machine shop and getting all these materials and lots of helpful sponsors. So what we do is any rookie teams and stuff that are in our area, they're welcome, and we actually bring them for kickoff and we teach them through it, but they are also welcome to send us files and things like that of things that they want machined. So a lot of these top teams do have extra resources, whether it comes from parts like electronics or motors and things like that. They can also help you machine things, which can be really costly if you have to go out and get it done at an outside shop. So that would be one of the best ways to still be competitive, but be able to actually be within your resources too. So definitely ask for help. The other thing, obviously, is important to have a lot of sponsors and things like that. A lot of different regions and things like that have grants that they can offer. But I think seeking out help from other teams is one of the best ways to be able to get more resources. Yeah.
Thank you.
Actually, in terms of investing or what to buy as like one of the things for any team, I think batteries are the most important. So we find that when we go to regionals and stuff like that, and if teams don't have enough batteries for all their matches, then they're actually not performing that well on the field. They might have a low battery issue. So I think the first thing to buy is actually batteries. Like we do the same. We try to buy batteries every 2 years. And then we use our old batteries for our practice robots and doing autonomous and stuff like that, so that at least in competitions, we have maybe 4 or 5 fresh batteries that are only used during those situations. Yeah. So batteries would be the main one.
Another question would be like your team, it's already quite experienced and recognized. So what is something that you can tell that you learn with the passing of time about the discourse and the building?
Sorry, I think you cut off a little bit there. Would you mind repeating the question?
Oh, sorry. Yeah. As an experienced team, what can you say that you've learned with the passing of time about the design of robots, like advice that you can give when you are designing a robot?
Right. I think the best tip is to keep things simple. So the reason why I say that is in 2015, when it was the tote stacking game for Recycle Rush, both our teams that are at our school, we had 2 teams, they decided to go really, really complicated. So we had 1241 who built a double stacker. So it actually would make 2 tote stacks in the robot because there was no size requirement that year. And then 1285 had 2 independent robots that had a wire tether in between for electronics. And so both our drivers were full drivers. Like it wasn't a tool operator and a driver. Both were drivers and tool operators. And they would have these 2 robots that would go around and perform the task. Way, way, way too complicated. We were not successful by any means because we couldn't score as many totes as we should have if we made a simpler robot. So a lot of our students in that entire year was very difficult because we had to constantly just improve. It was just constant design for the entire time to make things better. But if we chose something simple at the start, it would have made our lives much easier and we would have done much more successfully. But we learned a lot from that year because our students got a lot faster at designing because they just were under pressure all the time. So the next year in 2016, we made a much simpler robot. We made a tall robot that couldn't go under the low bar. We made simple arms, a shooter, and all that kind of stuff, so that it's all designs that we've done before that makes it easier. And so we were very successful because that 2016 robot that we had, which is this one here, which is this one here, that one was built in 4.5 weeks. So we had a lot of time to program before our first regional. We were able to build 2 robots so that we could have a practice robot too. And keeping it simple to this rather than going as complicated as 971 was probably the best decision. So I think keeping it simple is the best advice. Yeah.
Okay. There aren't any more questions, but
I have another question. Yes.
Okay.
Do you recommend building a test robot?
Sorry, I didn't get that.
Do you recommend building a test robot?
A test robot.
Yes.
Yeah, actually, let me show you guys something because it's pretty good for resources. So this robot here is for our 2018 game. And what we did was we actually built the test robot out of wood. And there are examples that I can put later on. Also, we did the same thing in 2016, where a lot of our test robot equipment was made out of wood rather than metal. So it's a lot cheaper. And we only put motors on things that we really needed motors for. So we didn't put motors on the elevator. We actually just put some holes. And you can see, like, if I expand this, there are just some bolts that are here in case we want to go higher with this carriage. And all you do is just screw it into place. So building a test robot doesn't have to be a full replica of your real robot. You could make it out of wood and still be able to test with it, rather than actually spending so much money and time in making a second robot. Making one robot is hard to do. Making 2 robots is actually pretty difficult too. And you don't know if your robot will work the first time. Even if you've designed and thought of everything, you may not know. So you might actually waste some money and resources building the second robot the exact same. And whatever change you have to do for the first one has to be implemented in the second one, right? So it's actually pretty hard to be able to do that. So we've had a lot of seasons where we've built the 2 robots and we've tried to figure out which one do you build first. Sometimes we've built the practice robot first and then build the real competition robot, so that anything that we had to change on the practice robot, we could put into the real robot. We've built it the other way, where we built the competition robot and then the practice robot second. We found when you have to do that, teams may not put as much effort building their second practice robot because the first robot's already done, right? And that's what you're going to competition with. So sometimes it's not motivational enough. So yeah, it's okay, but I highly recommend using wood for some of your testing and prototyping and practice robot things. So then it allows you to save some resources.
Okay, thank you very much. I don't think we have any further questions, but lastly, we would like to ask you, what would you have advice to a team that, because of the pandemic and everything that happened, stopped working?
Yeah, so
but they're coming back this year.
Okay, yeah, I think a lot of teams, if they're coming back this year and stuff like that after the pandemic and whatnot, you have to really find out how much you can actually put in terms of a time commitment, physical or even online. Just because if you're not able to go into your school or go into your meeting area or workshop or anything like that, I know in Canada, we have a lot of restrictions right now too, depending on different school districts. So some teams can only meet during lunchtime. And that means in the entire 7 weeks, that's actually only translates to like 35 hours to work on a robot. So that is not at all enough time. Like you can see those teams that do robot in 3 days and whatnot. So that's 3 days over 7 weeks time frame. That's not enough time at all. So you have to make sure that you build something simple or something that's competitive. So a lot of teams may have to change the way that they want to approach the season and define success differently. So if you get a drivetrain on the field that can intake the ball and maybe shoot into the logo, that might be a successful robot because of the time you had. And so you may want to make sure that your team is not stressed out trying to finish something before a competition, and making sure that you do check-ins with each of the students to make sure they're not exhausted. The other thing to also know is that meeting online is different than meeting in person. So having a lot of meetings online means that you may not have time to play around and have fun, right? Where you have something to like make jokes or things like that. So what we've found is if you have too many meetings and they're all work meetings, then it's not going to be fun. It's just exhausting that every meeting is something like that. So try to have fun days, try to have fun meetings where you don't have to do any thinking or anything related to the robot. We've had story time as one of the things where we have slideshows from our mentors or old students to talk about something funny that happened. We have a lot of students that build Lego and they make like, big pieces and stuff like that. So we have showcases like that where they'll just show us there's a Lego day and everybody shows what cool things they've made with Lego. And those that kind of things are really important in making sure that you're having fun during the season.